Hello, welcome. Name's Bill. Nice to meet you. Anywho, what's this video about today? It's about the universe. Moreover, the fact that dark matter does not exist. Dark energy is not a thing. And I'm going to try to articulate it to you as such. The reason they can't find dark matter, dark energy, is because they're trying to explain something. They're trying to explain a fundamental force that is causing the universe to not only expand, but explain expansion and all the rest. And because, not for lack of effort, but because they just don't know, they've assigned dark energy and dark matter as the reason for what they're not seeing. And I believe the reality is much simpler. Let's take light, okay? You can't see a beam of light until it is broken by, let's say, dust or moisture or something like that, where light particles reflect or collide with something to allow you to see them. That's why you can't see a laser beam from the side or a light beam from the side or any such thing without some medium that those photons are smashing into and reflecting off of. So what's causing the driving with the expansion isn't dark matter at all. It's not dark energy. It's light itself. It's radiation. Now, I have no idea how many different types of radiation there are. Okay? But radiation and light are the same thing. Okay? Light, the visible light that's reflecting off of me now, is just a form of radiation for which we can see. And radiation has different bands, wavelengths. Okay? Now, I won't say that means that different forms of light have different speeds. Although they could, because apparently all radiation, from what I've understood, all light patterns travel in waves. Okay? So we won't get into the whole particle wave difference. Point is, whether it's a limitation that's even light has or not, radiation is light. We just can only see a very tiny, tiny sliver of the band. Okay? The visual light that you and I are able to use to record, that reflects off of us, and all the rest, that's what we see. Okay? The whole white through yellow, whatever, red variants that we see, blues. But here's all you have to do. Even Hawking radiation. All radiation is light. The fact that you and I cannot perceive the different variants or gradients of that light doesn't really mean anything. It's all light. It's all radiation. Now, at the beginning, I said, hey, you can't see a light wave, right? So think about that. You take the sun, a sphere, right? And it's pumping out light. It's pumping out radiation. 365 degrees all the way around it, it's pumping it out there. Now, we can't see what's shining off the sun. We see the sun is emitting towards us. And during a lunar eclipse, even then, you have to use like a welding helmet or a special pair of sunglasses to look up at the sun in full eclipse, and you can see that around the moon there's the ring, and you can see the little jets of flame or fire or radiation that's spewing out of it. It's beautiful. It's amazing stuff, right? It's really cool. But so we're seeing that, and it's amazing. But you still have to wear the lenses because it's not quite perfect. And even if it was perfect, or even over perfect, you'd still see that ring, and it'd still be a problem because of gravitational lensing that occurs from the light coming up and around the plane of the moon, which does have gravity, although almost very tiny. However, it's enough to cause problems. So, instead, what you have to understand is that the whole universe is like that. Trillions upon galaxies, each having billions of stars, hundreds of trillions of light sources around. And some galaxies, as you look at them, the darkest spots on the map, the darkest spots, even when they focus the lens there and look long enough, what happens? They wind up seeing more galaxies. So space is full of light coming from all directions. Now, if you could take all that radiation, all of it, and we have a form of this, the heat map, the universe heat map. But take for a second. We can do this. Assign all radiation, all forms, all spectrums, a color or gradient. If the gradient's black and white, fine. If it's blue or red, that's fine too. But here's what you would actually see. Right here. White. White. Now you would see pure white if you were able to see light from the side. Pure white. If it's a gradient. If it was blue, it'd be pure blue. Red, pure red. Green, pick a color. Neon, I don't care. You would get a solid. If you assigned all different levels, from red shift, blue shift, from the neons to everything, if you assign them all as a visible spectrum, and you choose that spectrum as white or blue or red or whatever it is, that's what you're going to get. Now, here is what you'd most likely be able to see. If you couldn't see and that was just being able to view light in all directions, not just what's coming at your eye, but if you're able to visualize it. And here's what you'd see if you could see all the light coming to you, all the radiation. That's what you'd see. These dark spots, those would be black holes. The biggest, this would probably be us, our center black hole, and maybe over here you'd be able to see Andromeda. Who knows? Point is, you'd be able to see a black hole because it does not emit light. Straightforward in that way. Okay? It doesn't emit, it sucks in. Now it may have poles which eject light, eject radiation. Hawking radiation may come off, but whatever you're looking at, that radiation would be regressed back in. Because remember, light, not even light can escape a black hole. Apparently radiation can. But it's the Hawking radiation would dissipate at such a slow rate, you'd still see the darkness. You'd still see the darkness because it wouldn't be as intense, right? If it was as intense as it was going in, there'd be no black hole, right? Because the gravity would be enough to hold anything back. So Hawking radiation is relatively slow in comparison to the size and overall mass of a black hole. It ebbs off of it. So on black holes, maybe they would shimmer a little bit. Maybe they would blink. Hard to say. But that is what you would see. Now, if it were in reds or blues or greens, it would probably resemble more of a heat map because there would be hot and cold spots, but it would just be a variation of that red or that blue, whatever color you chose it. The white, you would have brighter spots and not as bright, but no dark except for the black hole. It's the only black you would be able to find on it. Why does this matter? Because it goes to show just how little we actually know. And when you can't say I don't know, you come up with bullshit like black, dark matter, or you come up with bullshit like dark matter, dark energy, things that make no sense whatsoever. It's not observable. This we can see. We can observe this. We have the technology to see it. Okay? And I've got got many more thoughts on this, but I'm going to try to keep it pretty summed up. So, when you see Neil deGrasse Tyson or some of these other folks talking about, the dark matter, the dark energy, they don't have a clue. It's the God of the gaps fallacy. All right? We don't know, therefore God. Well, they're just taking one more step and saying, we don't know, therefore dark energy. They made it up. It's a bullshit term. There's no reason to even suspect or think that dark energy or dark matter is anything other than some sci-fi woo. And that's all it is. But it's a placeholder. They'd be a lot better off if they just called it for what it is, a universe of light with spots of darkness, which are just black holes. All right, well, thank you everybody for tuning in. This is a short one, only 10, 11 minutes long, something like that. But I hope it made you think a little bit. And I will try to do more videos, and eventually over time the quality will get better. But I will try to I'll get that out to you and just share some of my thoughts. Some of them are going to be dumb, some are retarded, all the rest. But that's okay, because I can say whatever the hell I want, and so can you. And use critical thinking. It's massively important that people think critically. It's massively important that you take situations, and I'm not saying you can simplify everything, but common sense isn't common, and I wish it were, because real common sense can take you a very, very long way. And no, I don't view myself the way Neil deGrasse Tyson would say, and say that most people know enough just to be not to know they're completely wrong. I'm actually pretty decent at math, or at least I used to be, and the math checks out. I'm hoping that those who are better at it than me can take some actual time to think about what I've said about the universe of light and how it makes sense. I'll tell you what, I'm going to take a couple more minutes real quick and address the elephant in the room, which is how the universe is expanding. They blame dark matter and dark energy. It's light. Light is causing, or radiation is causing, the expansion of the universe. And it does it not uniformly, because of the hot spots, because there are brighter points of the universe than others. Okay? There are more radio intense areas of the universe. We know this. We know this very well just from our own probes sending out once they get past the outer regions of our solar system. The radiation is just super intense. We've got just hundreds of years of data on this. Okay, there's no denying it. There's no questioning it. It's just a fact. How does that pertain to what I'm saying? Is, let's say you take something the size of a postage stamp, a solar sail, and they talk about this, oh, let's launch one of these and we can reach another solar system, in however many years. Okay. I think you're wrong on that, because the problem is you have to, how do they accelerate it? They say they would accelerate it with either a moon or space-based laser, right, which sits in geosynchronous orbit or something like that, so they could maintain a constant light beam to it. a constant laser beam on it, and accelerate that using light, pushing it with light. It's a solar sail, boom, out into the reaches. And I think it would do quite well until it got to the edge of the solar system, but then you've got your not solar winds, but cosmic winds out there, and radiation. That's not just going to be, not just pushing it, but also pushing against it. And so you've got to accelerate that thing. Let's say you can get it 99.9% the speed of light. The entire time it's out there, it's slowing down. It's slowing down because of the radiation that it's hitting against. It's running into and running into it. The point is, you get two suns, and you take those two suns and you set them just outside of the gravitational forces on each other. And I believe that if you take those two spheres, those two balls of light, the two suns of equal size and mass and density, and you set them just outside the limits of what the gravitational pull would be on each other, and I believe they would start to rapidly push away from one another. I believe they would separate themselves because of all the radiation that both those spheres are producing in opposition to one another. If I look at a light, if I'm looking at, let's say, I look at the, oh, that's bright. Look at one of these high bay lights, right? I can still, not looking directly, I can see everything around it. Okay, so it doesn't take up my full field of vision. Okay, I can still see all the stuff around it. Okay, so that all that radiation's not hitting me. You have these two balls, but if it was looking at me, if I was a light, it would be able to see all around me too. The point is, it doesn't nullify. Okay, so instead of the lights coming and hitting each other, bam, can't go any further. Some of the light, a lot of the light, actually completely misses each other and then hits into the semi-solid plasma of the sun, and in a vacuum of space, okay, where they're not being where gravitational forces aren't the controlling factor on the two bodies, it's going to push themselves away. So it's not acting like two rockets. It's not a rocket. It's not propelling the suns out, because they're spheres, right? They're shooting off in all directions, so there's no propellant. It's a push. They're being pushed away from each other. And if you have two supermassive galaxies, right, that are far enough that they're not interacting gravitationally with each other on a big enough scale, the light from those two galaxies are also pushing each other away. They're not propelling away from each other, they're pushing away from each other. And when you take into consideration that the universe is nothing but light, radiation, and of what that map would look like, just a blank sheet, it's getting hit from all sides. So the brightest parts are pushing the hardest. That's why you don't need any woo-woo dark energy, woo-woo dark matter. It's unnecessary. The radiation, the light, the wave is going to do it all on its own. And it's going to do it a lot more powerfully than you think. There's no need, none whatsoever, for any woo-woo. That's simple. Well, thanks, guys. I appreciate you listening to me ramble. And like I said, my future videos should get better, I hope. Maybe I'll find a room or something like that where I can put stuff on the wall and not do this in a shop building. But I wanted to say it, so I said it. Y'all have a good day. Bye.